Thank you. Okay, so I know you all want to get out of here. It's long, so you want to go outside. So I could just stop talking, or I could bring outside to you. So, can I please have a recording from Anzac? It's 5 o'clock in the morning, June 6, 2014. All right, we're standing by a wetland. It's 5 o'clock in the morning. These are some of the species that we're hearing. There's about 10 in this 2-minute segment that I could play. I'm not going to play the whole thing, but the point is we got a lot of information just by standing there and listening to the soundscape. Now, I fell asleep. I had my bug net on, so I survived. And it's now 18 hours later. It's midnight. And let's see what happens at night. Exact same place, 18 hours, nothing in common. All the species detected are completely different. And what we are talking about here is the efficiency of monitoring. What we've got to now start thinking about is how can we take and find new technologies that allow us to get these nocturnal species, these diurnal species, these early spring species, these late summer species, and be able to talk about them in a coordinated and effective way. So that's what I'm going to talk about today. Sorry, how do I? Green's good. Green's good. Okay, so what I'm going to talk about is a developing group of people called the Bioacoustics Unit, which is part of the University of Alberta and ABMI, that evolved from a variety of projects that started about 3-4 years ago, even before JOSM came into existence. I'm the science director. Jim plays a role in it. Sean Morrison, Dan Farr, Monica Kohler, Hedwig Lankow are all members of trying to build this group of coordinated individuals who are trying to find a way to make basically recording of soundscapes a standardized approach for monitoring in Alberta. Now I've got a bunch of graduate students and technicians as well who are very instrumental in doing this. Now where did we come from? Well, we came from the fact that there's a lot of species that are already being monitored. ABMI, as Jim has talked about, monitors many, many, many species, but they were doing a fairly poor job of things that called at night, things that called in the early spring, things that maybe people viewed as rare. So in 2010, a group called the EMCLA, which stands for Environmental Monitoring Committee of the Lower Athabasca, was formed. And it was both an industry and a government collaboration to try and come up with ways to monitor rare wildlife on the oil sands leases. And the goal was to find the most cost-effective ways to fulfill APIA clauses on lease, at the same time to contribute to regional monitoring in a coordinated way. So first thing we did, took everybody's data from the old ways of doing stuff, put it together in a database and tried to use it. Found a lot of problems, all right? So we then said, okay, well, what could we do different? So we set out as a mandate, let's try to figure out how we could monitor these 3 rare species, Canadian toad, barred owl, and yellow rail. Now, these species, if you've ever tried to monitor them, they all have this wonderful behavior that they sing at night. Who wants to go out at dead of night? It's not so much fun. Add to this the problem, barred owls are active in March and April, Canadian toads are active in April and May, yellow rails are active in May and June, and you've got to go to the same place at least 3 times to be able to get any information on those 3 species. They're also in very difficult places to get to. That looks like a wonderful field of grass, but it's actually something that is every step you take, you need snowshoes or you sink through to your head, and you get very, very wet. So in the past, what people did was they went out, they're rare species, they wanted to elicit a response, so they'd play back the sound of those species to them, and they'd see if they'd respond. They'd do this in the dead of night, they'd go back 3 times, and the data wasn't really telling us much about anything. So what we decided as a group was to try recording. Now, recording technology has been around for a long time. People have been recording soundscapes since the early 1990s. In the old days, we used a really cheap speaker and a Walkman, and ABMI switched and used this technology throughout the 2000s, but in that technology, what they had to do was a person would move the recorder around. That was nice. We got good data. The data can be stored forever. People can listen to the recordings forever. There's lots you can do with it, but you're still having to go back and move these things all the time. So 2010 comes along, and people have now shifted. We've gone to a new technology called automated recording units, or automatic, or autonomous. There's all kinds of what A can mean. Be's whatever you want. The joy of these things is that they're programmable, and they're fairly cheap. You stick them out wherever you want, turn them on, program them to turn on whenever you want. So we can record 24 hours a day if we want. We can record 1 minute a day for 365 days. It's really just a matter of memory and battery. So you can program these things to do all kinds of things, put them in the weirdest and most wonderful places, and get a recording of what's going on. Now, ABMI in the past, 2007 to 2014, 10,000 recordings, 10 minutes each, about 100,000 minutes of data. It's very nice because it can be looked at again by different people to check its accuracy, those kind of things. This is what ABMI has now, 263 species, 167,000 records. But again, remember, they're moving these ARUs around. In 2 years, I collected 15 times more data than the previous 8 years of ABMI. I have over 1 million minutes of data. And I have so much data that I can't even deal with all of it. And the question is, what can we do with it now when we have that? So having more data does matter if you're worried about rare species. So what we have here is a graph. On the left-hand side shows what's called detection rate. And this is the probability of hearing a species on different days when you know that it's there. In other words, there's lots of times you will go, and if you go as a human and stand there for 5 minutes, 10 minutes, that you'll be there, the species will be there, but it won't call. And in fact, the vast majority of species, you will find 1 time out of 3 that you go there. And the big point of that is our accuracy of who's there, how many there are, when they're there, is actually relatively poor when we use humans. When we use automated recording devices, we get much more accurate estimates of what is actually present. Now this helps us, I'm not going to go through this in detail because I'm going to try to get you out of here fast, is to help us understand rarity. We now start to understand when species are rare, what is it that's driving it? And the main take-homes are this: species that call more often are easier to detect. Species where there's multiple individuals at a point are easier to detect. Species that are regionally more abundant are easier to detect, and species that call during the day are easier to detect. But we can take this data now, and one of the really great things that we're just working on right now and should be done in about a month or two, is we can actually now compute how long you have to stay to prove something isn't there. So you might need 2 days, you might need 3 days, and at that point you can say, I'm fairly confident there is no yellow rail or some other species of concern in that particular spot. And that is very important when we're talking about mitigating impacts and trying to avoid certain places because rare species exist there. We need to know for sure they're not there. Now listening takes a lot of time. Okay, I've got literally my entire lifetime worth of data. If I listen to all these recordings for the rest of my life, I still will be listening before I die. So we need a better way of actually dealing with all of this data. So one of the things my lab is working on quite hard right now, and we're trying to build partnerships with computing scientists and a variety of other things, is automated recognition. Computers can identify acoustic signals, and what they do is they run through and they look for a picture of, essentially what they look for is a picture of the species. They're trying to match what what's called a spectrogram looks like. So this is what the signal looks like, and I'm going to search through this recording and see if I can find it. Now there's still lots of error. We're getting better and better and better at it with computing, but there's still lots of error because sound is incredibly complex. But what we found is that people can check recordings very, very quickly. They can go through about 30 what are called flags a minute and say, yeah, the computer was right, no, the computer was wrong. And the key question is, are people more efficient? So I'll show you this one as just an example of kind of where this is going. So this is the lower Athabasca region. Sorry, I don't have a pointer, but this area, think Cold Lake all the way to Fort McKay is where this is. The red dots on there indicate, and the white triangles indicate everywhere that we've detected a barred owl. The white points are the ones where we heard them. A human was put on a pair of headphones and heard them. The red ones are the ones where the computer found them. Way more information, way more places found when we actually use the computer to do it. So the efficiency part of this is even though sometimes the recognizers aren't that accurate, they give us a lot of false detections of owls. When a human checks them, about 0.18 barred owls are found per minute of time spent doing work. If a person just puts on a set of headphones and listens, the 0.002. And if you go back and do the old conventional way, that is go out in the field, push play on a barred owl call and see if the barred owl comes, it's about 0.003 barred owls per minute of effort. So it's an order of magnitude improvement in our ability to find these species. Canadian toad, yellow rail, 2 other species we're working on, very similar. Now, what we've been trying to do with the data, the actual stuff, so that's trying to get in the background why we're using them and how we're using them, but we're trying to use these to try and figure out information about what's going on about certain species. So the big reason we did this in the first place was for a species called the yellow rail, which there's appeal clauses on most of the mines to actually monitor this species. That is the data from 1900 all the way through till when we started. Before we started, the detections you can see, that's the number of detections per year of yellow rails in the lower Athabasca. It's like 1, 2, 3, 4. Even when people put in huge efforts, in other years they got up to 30. And with ARUs, we have now found them at over 100 locations. They're far more common than we thought they were, but it still took a huge amount of work to find them. What's important is the computer recognition was a big part of helping us find more and more and more and more. We're able to now start mapping out the habitat, and we've got some pretty good ideas of where to look. The southern edge of the range near Cold Lake, Lac La Biche is an area of particular importance, and that's important from the oil sands mineable perspective because the original reason for monitoring them in the first place was people thought that's the only place they really were. Thankfully, they are in more places than that, but that does still mean that we've got to take a look at where we're going to look at. So that's what we're continuing to do is get trend monitoring. There we go. So one of the things to highlight, yellow rails still are rare. The other thing that we can now do, and I'm going to try to pick up the pace to make sure we get out of here fast, is what we've been able to show now is unlike when people do it. They go out for 5 minutes, they maybe push play, maybe the rail calls when they're there, maybe not. We don't really know when you get a 0, when a human does it, what that really means. Well, if you leave an ARU out for 3 weeks and never, ever, ever, ever hear a yellow rail on it, you can be really confident that it wasn't there that year. And what we've been able to do now is look at the temporal variation of these birds, and they actually are somewhat dynamic, and it depends on the water levels that exist within the fens that they live in. Now, the other bonus was when you did the yellow rail survey, as they used to do in the oil sands, that's the only data you got, data on yellow rails. This is a list, and I'm sorry you probably can't read it from the back, but it's a list of all the other threatened species that we found in the McClellan Lake area. And so by using these ARUs, we're able to get data on a lot more species and do the rare species like yellow rail. Now, we also have been using these things with companies directly to try and address questions about impacts. So we have a design element to the project where we're looking at no noise areas, no light, low to moderate footprint, ranging all the way up to the highly developed sites to see how certain species respond. I have one student working on Canadian toad, one working on barred owl. And what we've been able to demonstrate with the barred owl is that barred owls are avoiding areas that are very noisy and very lit up, but they are actually doing quite well and quite regularly use areas with linear features, well pads. And those are probably because those are areas where they can hunt and get prey and things like that, whereas the noisy lit up areas are places where they're probably not able to do that. Now, we're also doing some work trying to take this technology to the next level, which is figure out exactly where animals are. So this is a typical well pad, and one of the questions we have is how do animals use those? Well, if you do a regular point count, you can't figure that out. All you know is I'm standing on the well pad, I hear birds, some of them are in the forest, some of them are on the well pad, I'm not sure exactly where they are. So I have a student who's trying to figure out exactly where the birds are. Are they on the well pad, on the edge, or in the interior? So one of the cool things about ARUs is that some of them are GPS time synced so that you know exactly what time it is to the millisecond. And what you can do with that is you can actually triangulate the exact position of where organisms are because sound arrives at each one of the ARUs at a slightly different point in time. So Scott's been able to actually figure out exactly where a bird is located relative to a well pad, relative to an edge, by using this technology. And basically we've got it down to if you put 4 ARUs 50 meters apart, you can figure out plus or minus 13 meters exactly where the animal is. So we can learn things about well pad restoration, linear feature restoration, and how animals are actually starting to use those. Now, going forward, ABMI has now switched to this technology. That's given a huge number of benefits. On the systematic grid in ABMI, you will now get from March all the way to July data on everything that is there. So that now means we're now monitoring owls, we're now monitoring rails, we're now monitoring toads, amphibians, all the songbirds, and anything that makes a sound. But the thing is, ABMI still is on a systematic grid. It doesn't go to all the habitats. And so what my program does is kind of fills in those holes. It goes to those habitats that ABMI does not sample well, and those are the habitats maybe where some species of concern we have to put the ARUs to make sure that we're monitoring them well. Now, just to highlight again, I'll skip over that. But this is the nighttime curve, and it will get at least 35 to 40 new species and get everything that ABMI did before for the same or less cost. The The other nice thing about this is it's very easy to engage communities in their use. We've worked with a variety of First Nations people to kind of discuss where they want to monitor, why they want to monitor. We've given them the ARUs and they've put them out. Now, one big thing is, as I said, there's a huge amount of information flow coming here, and we've got to keep track of it if we want to make it useful. So COSIA has sponsored us, in conjunction with Environment Canada, to build a data system to store all these recordings that people will be able to access, both the general public, companies, and anyone who wants to use it. The basic idea is this: you'll be able to log into a website. The website will show you a visual picture of the sound. You'll be able to play it, listen to it if you want. A professional and/or the computer will have identified the things that are on it. You can check them if you want. You can argue with them if you want. There'll be a map where you'll be able to click and get, this is what's been recorded there, here are the recordings, things like that. What we're trying to work out right now is the way that that data will get stored. Would it all go in one central place? It's a huge amount of data. We need like a server farm for it. Or do individual people store it on their individual servers and the computer talks to it that way? So with that, I'd just like to thank a lot of people, a lot of companies, the Joint Oil Sands Program, Environment Canada, Government of Alberta, ABMI, for all their support in helping the bioacoustic unit get up and running. And with that, I'll let you really go outside and listen to birds, but we'll stop there.